Welcome, everyone. It's a great pleasure to have Alex Nielsen here with us, even if remotely, and even if under these dire consequences and circumstances for all of us. Alex is a colleague, a collaborator, and an old-time friend. He did his bachelor's in the Imperial College in London, a PhD in New Zealand, postdoc in Korea, another postdoc in Potsdam, and later Hanover, the Albert Einstein Institute, and is now a professor of physics in Stavanger University, Norway. Alex will tell us about searching for black hole echoes in gravitational wave data. Please feel free to ask questions at any time. Go ahead, Alex. Thank you for being with us.
All right, thanks, Alfred. Hi, everybody. Yes, so hello from Norway. The picture I have on my backdrop here, hopefully you can see it, is one of the fjords that's near here. This is the Lyse fjord. There are a few people, if you look very closely, you can see there are a few people for sort of scale. Right in the middle of the picture, there's a couple of white lines that are boats on the fjords, just to give you an idea. This is actually the fjord that is providing most of our electricity here in Stavanger. So up at the back of the fjord somewhere, there is a hydroelectric power station that is producing most of our electricity. Okay, I'm going to talk about echoes, searching for echoes. Up front is the boring, disappointing summary, which is that I don't think that we have detected echoes yet. So basically what I'm going to tell you about is the non-detection of echoes. So just to be upfront about that. Okay, so we now live in exciting times in astrophysics. We have increasing observational evidence for objects that are at least behaving like black holes. At the top left, we have gravitational waves. This is basically mostly what I'm going to be talking about. In the middle there, we have the observations of stars going around the black hole at the center of the Milky Way, the S stars. This won the Nobel Prize in 2020. We have on the top right there, we have the image of M87, the center of M87 that was in the news a couple of years ago. And down at the bottom left, we have a sort of artist impression of X-ray accretion disk. These are probably the first indication that there were actually black holes in the universe from X-ray observations from black holes that are sucking matter off of other stars into an accretion disk, heats up in the accretion disk and gives off X-rays. So we have all this now evidence, data of objects that are behaving like black holes in various different ways, in various different regimes. The question we want to ask is, are these objects really black holes? I'm going to talk mainly about gravitational waves. This picture now is part of figure 1 of the LIGO detection paper of GW 15914. This was the first gravitational wave event observed by the LIGO observatories. This is quite a familiar image now. This is the image that a lot of people are getting tattooed on their arms and on t-shirts and on their research center logos and everything. This is becoming a very well-known image. It shows the strain amplitude, the oscillations as a function of time as you go forward in time. What I want to emphasize for you, for those who are not too familiar with this, is that this waveform can be divided up into different regimes of interest. I put 3 vertical blue lines here to approximately divide this waveform up into different regimes. On the left, to the early times, there is the in-spiral phase. This is when you have 2 black holes, 2 separated black holes that are orbiting around each other. This is mainly analyzed by what is called the post-Newtonian approximation. So the 2-body problem to describe 2 bodies orbiting around each other has not been solved in complete generality. In general relativity, there is no analytic solution. So we have to use approximation methods, and we use this approximation method called post-Newtonian or PN approximation to describe the in-spiral. Then there is a regime where the black holes get very close together and they eventually merge into each other, crash into each other. This is very nonlinear. You can't use approximation methods to describe it. You have to use numerical relativity. This is the merger regime. second one from the left, merger, NR. NR stands for numerical relativity, so you simulate this on a computer. Then the third regime is what is known as the ring down. So you form a black hole, eventually the two black holes merge together. They form a single black hole, it is a perturbed black hole, but that perturbed black hole rings down like a bell very quickly by emitting what are called quasi-normal modes, Q and M. This is the ring down phase. And then the fourth regime, the one that is right on the right, is where there is potential of seeing echoes. Now, in standard Einstein general relativity, there are no echoes. So this is the regime where the signal should die away and there should be basically no signal. That is what you expect from standard GR. But there is a possibility, if we are not, if the universe is not standard GR, that there are these things called echoes. And that is the main topic of what I'm going to be talking about today. So right on the right of this diagram, after all the merger, after all the other signals that we have detected, is there something else happening that we haven't, that is not part of the standard model from GR? Just to give a little bit of background about the other regimes from the in-spiral, so we can constrain all of these different regimes using different things, different techniques. This one here is from the archive. Me and collaborators last week, constraints on the in-spiral. You can introduce some non-GR parameters into this post-Newtonian system, and then you can go and look at the data and constrain them. And what we did here, we actually did this. This is actually not for a black hole system. This is for the binary neutron star system, GW 170817. But we managed to come up with a set of uncorrelated non-GR PN parameters. You can see that they're non-correlated by, in the images here, you see that all of these yellowy orange circle blobs are roughly circular. And by doing that, we can vary all of these, each one of these post-Newtonian terms has a coefficient, and we can constrain the deviations of each of those from their GR value. And the one that we do best is this delta psi here, which we constrain to about 3 parts in 1,000. So it is reasonably well constrained.
What's the red line? The red contour?
The red contour is the contour that passes through the GR value. So the GR predicted value for all of these constraints is 0. And so that is the level contour of the posterior that passes through the GR value. So that is basically how much of the posterior, how far out in the posterior do you have to go from the median to find the GR value. If that gets very, very large, then you're doing very, very well. Another paper from my group from last year. This is now for the merger phase. What you can do in the merger phase, because it's non-linear and there aren't very many easy ways of finding out what the predictions are, is you just take the prediction that you get from the numerical simulations, from the computer models, and you subtract that from the data, and then you look to see if there is anything left. And if there is nothing left, then you say, well, we're probably picking up most of the signal because we're modeling it well. This is a piece of work I did with some collaborators of mine. This one is actually not very sensitive to these kind of deviations. We did it like this way because there are some people in Copenhagen who were at least previously making a lot of noise about how they didn't believe the gravitational wave observations. So we actually went through and sort of did it in great detail. What you see here is you see time running along the bottom. On the x-axis, there is a correlation of the original data. So the correlation between the two detectors, the LIGO, the Livingston detector and the Hanford detector. When you have an astrophysical signal, you expect that correlation to be large, or in this case, negatively large. And if you just have noise, you expect it to be not correlated at all. And you can see the dark blue line, which is the one with the original data. There is a strong negative correlation where we expect the signal to be, as shown by the yellow plot below. And what you see with the orange dotted line is you see the residual correlation. That is the correlation which you take away the signal. And you see that it's not actually that large, and it's actually consistent, very consistent with the sort of noise fluctuations that you expect. So that isn't really a direct test of the merger phase, but it is the strongest part of the signal is suspected to be the merger. And so if you're subtracting all of the signal, you are probably most sensitive to weird stuff happening in the merger. If anything would go wrong with the standard GR prediction, you would expect to see it maybe with this kind of test first. And the last one is the ring down phase constraints. This is a paper that was on the archive yesterday. When a black hole rings down, it emits gravitational waves at certain different frequencies, certain different ring down modes. It has long been known that there is a 2-2 mode. The dominant mode is the 2-2 mode. This is the one that you see on the far left here. This is for the event 190521, very high mass system. So the 2-2 mode is the one there on the left. You see that nicely resolved in the frequency at the top, the gray plot there. But then this new blob here at around a frequency of 100 Hertz, this is a new ring down mode. This has not been seen before. And this is corresponding to the 3-3 mode in general relativity, the 3-3 mode of a Kerr black hole ringing down. This is a nice test of GR and the Kerr prediction for the black holes, because if you have a Kerr black hole and you perturb it, then you find that the mathematics suggests that all of the different modes should depend on only two values, the black hole's mass and the black hole's spin. So if you measure lots of different modes, each of the modes you measure a frequency and a damping time, all of those values should all be consistent with the same mass and the same spin of the underlying black hole. So this is in some sense a test of the black hole no-hair theorem, and we are finding a 3-3 mode that is basically lying right on top of where the GR Kerr prediction suggests it should be. We actually constrain the frequency of this 3-3 mode to be within about 10 Hertz of its GR predicted value.
How much SNR do you have for the 3-3 mode?
The SNR in the 3-3 mode is about 4. So it's not a lot. There is about 11 or something in the 2-2 mode, about 4 in the 3-3 mode. But the Bayes factor preference for 2 modes over 1 mode is about 40 times, 44 times or something. So it is strongly preferred that there are 2 modes in the data rather than 1 mode for this event.
And this is just ring down?
This is just ring down. So we are actually gating out all of the merger, removing all of the merger, and just looking at times after the merger to look for these ring down modes as damped sinusoids. We have there is a little bit of possible evidence for a 4-4 mode as well, and maybe even the 2-1 mode, but it's not very strong. So we are going here in this paper at least with the strong evidence of the 3-3 mode. As you can see on this plot here, the green band would correspond to the 4-4 mode, and at least at this time there is nothing at the 4-4 mode, so you don't see any 4-4 mode.
And what's the blob around 5-5? Is that just the outskirts of the 3-3?
Yeah, that's the 90% credible interval for the 3-3 mode, or it's just looking for a single. What it's doing is it's looking for a single mode in that frequency range from 80 to 256 Hertz. And the gray dashed line is the 90% credible interval for that frequency. So it's kind of seeing everything in that mode. But
is that a harmonic of the actual 3-3 mode? It looks it looks to be about twice the frequency.
No, it's probably not a if there is a harmonic. Well, if there is a GR harmonic, the GR harmonic for the frequency is very, very close to the 3-3 mode. So it wouldn't,
you're talking about the
200 Hertz.
You're talking about higher end harmonics.
Yes.
I mean like a data analysis harmonic. If you just see an analysis gives you something at twice the frequency.
No, I don't think so. Yeah, I mean, numerologically, you could say, well, maybe the frequency matches. But on a data level, I don't think there's anything to say whether it is or it isn't.
Okay.
So that was on the archive yesterday. What we want to know is, are these objects really black holes? There is this very nice picture that the Portuguese group from Lisbon put out of this little wiggly line here, which is supposed to represent a ring down of a black hole, and underneath the French for "this is not a black hole." And they are emphasizing to everybody that just because you see a ring down, and just because you see something that looks like a black hole ringing down, this is not a definitive proof that there is a black hole, that there are other models that could reproduce such a signal. In particular, any model where everything is collapsed within a light ring will give a ring down signal. So just seeing a ring down in and of itself is not definitive proof that you have a black hole. And of course, the question of what is a black hole, whether you have a black hole or not, that depends on the definition of what you mean by a black hole. Black holes are typically defined by their horizons, so you would typically associate certain properties with the horizons. There are models that exist that do act a lot like black holes. For example, they have ring downs. For example, they merge around each other. They will have accretion disks. They will have S stars. They will be compatible with most of our observations, but they don't have horizons. Typically, these models are ones where an object is very, very compact. It is so compact that it's almost a black hole. It's just a little bit bigger than a black hole, and that stops it from forming a horizon. And there are various things that stop it from collapsing to be a black hole. These things are called, in the jargon and the literature, they're called ECOs, ECO. This is exotic compact objects. This is not quite the same as echos and echoes. Echoes are the signals, which I'll talk about in a minute, the signals that we can search for, and echos are the objects themselves, the exotic compact objects. So this is all driven by this notion of a black hole horizon. The standard definition, the definition you find in textbooks nowadays, is that of an event horizon. This was introduced by Stephen Hawking in 1971, amongst others, when he proved that there is a second law of event horizons. The area of event horizons is always increasing. But the event horizon, the way that Stephen Hawking defined it, is it's defined in this, he's used this very religious word to describe how the definition works. It's teleological definition. That is to say that the definition requires, it is the boundary of that part of space-time that cannot send signals to infinity, right? And what that means is, in effect, is that in order to locate a horizon, an event horizon, you have to know how your space-time is going to behave all the way out to infinity. You have to know the full future of your space-time. You have to know the future, and the event horizons depend on things that happen in the future. They are teleological in the sense that they know something about what is going to happen to them in the future. They react to future events that they even in principle couldn't possibly know about because they're not in their own past light cone. So that was the definition that Stephen Hawking introduced. Many of you will know about Jakob Bekenstein in 1974, proposing that the area of a black hole is actually a measure of the black hole's entropy, this famous formula that relates the entropy of a black hole to its area. That seems then to give some physical meaning to the area of these black holes. They're not like hard surfaces like the surface of an orange or the surface of a planet. They are some region in space-time that you define as the horizon, but this Bekenstein relation gives a very physical interpretation of that area as a measure of the entropy. And then, of course, because this sets up the notion of black hole thermodynamics and the notion of entropy, people like to ask, well, is there a statistical mechanics explanation for that entropy relation in the same way that there is a statistical mechanics explanation for thermodynamics in terms of microstates, atoms, things like that? Are there microscopic degrees of freedom of the gravitational field that give rise to this entropy that we relate to the area of the black holes? Also in 1974, there was this thing called the polar vacuum. If you take a star just sitting there on its own, and you say, what is the quantum field state? What is the state of a quantum field around this star? The standard thing you would do is you would ask for a quantum state that is consistent with the symmetries of the star, of its source, and you would write that down, and you would find out what that quantum state is, and that quantum state is the Bohr vacuum. And that's all very good. That's all well understood, and it doesn't have any massive implications for astrophysics. The only problem is if you take that star and you make that star smaller and smaller and smaller, eventually, when you take that star very close to forming an event horizon, a horizon, a black hole, that Bohr vacuum diverges. The expectation value of the stress energy tensor in the Bohr vacuum actually does diverge, in which case you move out of the regime where you can kind of ignore quantum effects and you can ignore the effect of these quantum fields, and you enter into a regime where you have to introduce them into your Einstein equations, and you have to worry about how these quantum effects, quantum fields will back react on your space-time and modify its dynamics. 1994, another highlight was this paper by Parantani and Peran, who actually managed to simulate in 4 dimensions the collapse of a black hole and its corresponding evaporation through Hawking radiation, and to try and understand how this is going to work. These numerical simulations are not very easy to do. And it's an area that I at least feel is kind of under developed, in that we actually would be good to see a lot more people working on this area and understanding how, for example, small changes in your initial conditions can affect how you form a black hole and can affect how the quantum state evolves, and then can back react onto conditions of forming black holes and how they evaporate. In 2012, there was this group in the United States, on the west coast of the United States, who came up with a theorem that says if you assume unitarity, you assume that black holes, when they evaporate, they basically conserve information, nothing gets lost, and you assume effective field theories, which is something that everybody seems to think is a reasonable thing, that there is a low energy effective description of how the universe works, at least outside the black hole. And you assume this condition they called no drama, that when you fall through a horizon, nothing special happens. They actually showed, or they claimed that they showed that these 3 conditions, these 3 assumptions that everybody would probably say are reasonable, that they are inconsistent. One of them, at least one of them, has to fail. So either there has to be a failure of unitarity, in which case information could be potentially lost into black holes, or there has to be a failure of effective field theory, in which case whatever is quantum gravity, high energy, degrees of freedom play some role in our low energy description of the universe. Or when you fall towards a black hole, something special has to happen, and you don't just fall through the horizon without noticing. Possibly you get burnt to a crisp, as they call it, in what they call as a firewall. So the guys who proposed this actually said the weakest of those 3 conditions is this no drama assumption, that there's nothing special going on at the horizon of the black hole, and that's probably the one we should give up. And so probably there is something special going on in a black hole, and the question is, can you observe that? Does that have any observational implications? There is also the Penrose singularity theorem. He won the Nobel Prize for this in 2020, or part of the Nobel Prize. And this proof that when you have horizons, that they form singularities in general relativity, this actually relies on not event horizons forming, but on things called trapped surfaces. So this was introduced by Penrose even before Hawking defined event horizons. This is a different notion of what is a horizon. This doesn't depend on this sort of teleological definition of I can never send signals to infinity. The notion of a trapped surface is a very local condition. It is a surface for which instantaneously the light rays are not able to expand away from each other, but are sort of contracted and directed inwards towards the singular region. So this idea of Penrose, which is the foundation of his singularity theorems, this doesn't. There is a gap between that and Hawking's definition of event horizons, because Penrose's proof depends on trapped surfaces, not event horizons. Then the last thing I want to mention in this sort of random random walk through theoretical ideas about horizons is this work by Jeff Steinhauer up in Haifa in Israel, who he actually builds analog black holes out of Bose-Einstein condensates, and claims that he observes an analog to Hawking radiation in his analog black holes. Obviously, it should be clear that in his lab, he doesn't have event horizons in his lab. He has something else, but he is seeing something like Hawking radiation from his analog black holes. And there are other groups in Canada and the UK who also claim similar things with also slightly different, but similar analog systems. So it seems like things like Hawking radiation possibly are not directly tied to event horizons. Possibly other ideas, for example, Penrose singularity theorem suggests that other horizons might play a role. This no drama condition suggests that there is a way of telling where the horizon is. And if you mix that in with Penrose's idea of a trap surface is something you can locally identify. There is kind of theme running through this that says that maybe thinking about black holes in terms of horizons is not necessarily the most profitable way to think about black holes. So that is the theoretical motivation. That is, you can have whatever opinions you think about the theoretical motivations. It's all theoretical. What I'm going to talk about mainly is observational evidence and observational tests that one can perform. What I want to emphasize to you guys is that the models that we are testing, they're not just there to parameterize our ignorance about what is still not ruled out. They're not just trying to fill in the gaps between what the experimental constraints are and what we think the theory is. There are actually physical motivations for thinking that there might be something interesting happening and that there is something worth going after observationally. For example, one of these is to take seriously this thing called the conformal anomaly. This occurs when you have quantum fields acting on even dimensional spacetimes, in particular 4-dimensional spacetimes. You have this thing that occurs called the conformal anomaly. There is a breaking of your classical symmetries in the quantum theory. People write down effective actions to describe this. These effective actions tend to diverge on horizons when you form horizons. So they tend to suggest that there is this conformal anomaly. And if you describe it by a one-loop effective action, that it does diverge, its stress energy tensor diverges when you try to form a horizon. So there is something possibly physically going on when you try to form a horizon. And then also this issue of the information paradox or the information loss, where several groups have suggested that there should be something special going on at horizons to stop this loss of unitarity, to stop information from being lost down black holes. So there are theoretical motivations for this, and that's what I'm gonna talk about, the observational constraints. Okay, I'm going to talk about gravitational waves. There have been observations without gravitational waves. They've been going on for at least 10 years now, in particular using these accretion-dominated advection flows. So these are black holes that have accretion disks. There is matter spiraling down the accretion disk. At some point, it reaches the inner edge of the accretion disk and then kind of falls directly into the black hole. What happens if you watch these X-ray sources for a while, you see they go through these soft states where most of the X-rays are coming from the accretion disk, and then that sometimes turns off or gets suppressed, and it goes into what's called a hard state, where it is dominated or well modeled by most of the X-rays coming from this material that is falling directly into the black hole off the innermost edge of the accretion disk. People can go out and look for this, and they can measure how much X-rays are coming out of these systems when they're in these soft states, in these hard states. And what they find, this is what is on the right, they find that the luminosity, when they plot the luminosity against, for example, the orbital period here, they find that there is a clear separation between objects that are accreting onto, well, when there is material accreting onto an object that has a hard surface, such as a neutron star, and material is accreting onto an object that we don't think has a hard surface, such as a black hole, there is a clear separation in their X-ray luminosity. And this is interpreted by this material is falling down advecting onto the object. When it hits the surface of a neutron star, for example, it heats up very, very rapidly, smashes into the surface, and then gives off a lot of X-rays. If it's falling into a black hole, it's just literally just disappearing down the drain, and there is no dominant contribution to the X-ray signal from that. So there is this observed separation between neutron stars and black holes, also white dwarfs. Part of the reason why this works and why this is an interesting probe is because there is actually a logarithmic suppression of how long it takes for any signal to come out from a region near a black hole. So this is actually a calculation you can do in a first GR course. When you learn about the Schwarzschild spacetime, you learn about radial geodesics in the Schwarzschild spacetime, you can calculate how long it takes for a light signal to travel from some radius to some other radius in the Schwarzschild spacetime. When you do that, you'll find that there is actually a logarithm that comes in, which means that you are actually sensitive to things that happen very, very close to the event horizon. Right? In the limit where you try to send a signal from the event horizon out to infinity, it never gets out. But if you move only a very small distance away from the event horizon, even a Planck distance away from the event horizon, it actually doesn't take very long to get out at all because of this logarithm. So there is this formula down here on the left telling you the time it takes to get out from the black hole relative to if the black hole wasn't there. It's a logarithm over the ratio between the distance that you have to send the signal, so the distance from the black hole to us, divided by the radius from which you are away from the event horizon. So even if you put in, for example, that the distance is 500 megaparsecs, for example, like GW 150814, 150914, or you put in that the light is coming from a Planck length away from where we think the event horizon is. You put it in, because of the logarithm, it actually only takes milliseconds longer to get out from a Planck distance away from the horizon than it would do if there was no black hole. Right? So these signals, if there is something, if it's hitting something as the matter falls down, if it's hitting a surface, even if that surface is only a Planck distance away from the event horizon, we would see the X-rays coming out. We would see the effect of that hitting that surface. So this is actually, these probes are actually probing right down to the very vicinity of the horizon. So even if you have some fanciful quantum gravity theory that says, oh, there are only modifications at Planck scales of the horizons, they're actually observable and in the observable, within observable reach. So that leads me into the basic idea of echoes. What happens with echoes is you have some gravitational waves. Some of the gravitational waves in a binary, they're produced in the space-time around the binary objects. Some of it escapes out to infinity and we observe it. Some of it is directed down inwards towards us, towards the black hole even. And what happens is that energy in the gravitational waves that's directed down towards the black hole, if there is something, some structure down near the horizon in such a way that some of that energy can be reflected from that structure, some kind of surface or anything like that, then that gravitational wave energy will get trapped in a kind of cavity between that surface. So here on the left with this plot, if there is some kind of firewall or membrane, it will form a kind of boundary. And there is also in general relativity this thing called the angular momentum barrier. This is standard GR prediction. Those two things together will form a kind of cavity for this gravitational wave signal to propagate in. And each time it reflects off one side or the other, some of it will be transmitted out. And each time it is reflected off of the outer angular momentum barrier, some of it will be transmitted to us. Right? And that is what we look for. We look for those kind of echo signals from this gravitational wave propagating around in this cavity. So on the right here, I've shown a kind of schematic of what the waveform would look for that. On the far left-hand side, there is the standard GR in-spiral merger ring down part. Here, that dies away, that is expected to die away. In GR, it dies away and never comes back. But if there is some surface down there by this by the horizon, then there will actually be little pulses that come out later that are these echoes of that signal. And we go looking for those echo signals. That's what we go looking for. Right? And these waveforms are called IMRAs. They stand for in spiral, merger, ring down, echo signals. They are not IMRIs and they are not EMRIs. IMRIs are intermediate mass ratio in spirals. EMRIs are extreme mass ratio in spirals. You'll see these acronyms bouncing around in the literature. They do not mean the same thing. They sound the same, but they are not quite the same thing. So that is what we look for in the data. We look for these IMRA signals in the data. There are ways of calculating what these signals will look like. In the limit of very, very compact objects, the multiple structure of any object, if you squash it right down to very close near the horizon, its multiple structure will approach that of Kerr. So you won't notice anything unusual in the ring down signal. You won't notice anything unusual in the orbits of the S stars. You won't notice anything unusual in the black hole shadows of, for example, M87. But if you consider a small perturbation on those kind of Kerr backgrounds and you propagate it around linearly, you impose some kind of boundary reflectivity at your innermost boundary, at this possibly firewall or membrane, the reflectivity would be equivalently equal to 0 in general relativity, but doesn't have to be 0. You can actually come up with some analytical templates, and there are a bunch of groups here who've been working on this. These templates are actually getting quite sophisticated now, using analytical methods, using perturbation methods. They do consider perturbations just acting on a Kerr black hole. So there's not a full non-linear numerical simulation of this, but even the numerical groups are starting to pay attention to this now. And there is actually a group in Rome now that is beginning to simulate these kind of echo signals using numerical relativity. So we start to understand there is energy floating around. That energy is back reacting on the black hole. Some of it is getting transmitted. Some of it is getting absorbed. This has nonlinear feedback effects, and you have to include everything, and it gets all kind of complicated. So the progress is advancing in predicting what these things would look like.
What's the group in Rome?
Paolo Pani's group. So he has a student who has a supergravity n equals 2 supergravity model that they have now coded up on a computer and can simulate. And he claims that they see echo signals from this. They don't have very much control over how the parameters in the original supergravity model relate to the parameters of the echo signals yet, but they are working on it, and they are heading in that direction. So we are actually entering into a regime now where we're going to move away from these linear perturbation analytical calculations, I suspect, to this is going to be numerical relativity in the not too distant future. I can't remember the guy's name at the moment, but I can look it up for you. I can send you the reference. Okay, so there are at least theoretical predictions for what these echoes would look like. Using the theoretical predictions, we can go and look for them. This is a big long list here of groups that have done these searches, looked for these echo signals in the data, starting at the top with Abedi, Daikar, and Ashodi in 2016. What I've tried to do on this plot here is capture on the right-hand side some qualitative statement about how confident they are that they have or have not seen something. So the guys at the top were announced in 2016. They had tentative evidence for these echo signals, so everybody got very excited. Lots of people wanted to go and look for themselves. There was another group that came out shortly after who said they also had evidence for echoes. Then where me and Offek get involved is this Vestervec Plus paper in 2017. That's with Offek and me and some other people in Germany. We went and tried to reproduce the results of Abedi and friends and we found low significance for echoes. We didn't think we were seeing echoes. And then there was an argument backwards and forwards between us and them. They came up with another paper where they looked at the BNS signal, the binary neutron star signal, where they said they had tentative detection. They were even more confident that there were echoes in the binary neutron star system than in the binary black hole system 15914. Then there were another bunch of groups who got involved in various different ways, using various different methods. Some of them were using what are called model searches, where they had a specific model for what the echoes would look like in mind. Some of them were being a bit more agnostic and were trying to just look for something more generic called unmodeled searches. People looked at different parts of the data, different events. This story went backwards and forwards for a while. I don't know if you look at these qualitative statements here, whether we are moving from tentative evidence, and as you go down, the evidence sort of starts to fade away, and there's low significance, and then not much evidence, and then really not quite much evidence, until you end up right at the bottom with the LVC's recent paper from last year with no evidence. So maybe there is a trend. The community is coalescing around this idea that there is no evidence of echoes in the data. That's certainly where my position is. I don't think that's where everybody is. There are people who are still claiming that there's evidence of echoes in the data, and particularly this Oldham guy in 2019. He put out a paper with more evidence, yet more evidence. And this review article that is at the bottom, Abedi, Afshordi, Naritaka, and Wang in 2020, they have a review article where they survey all of these results, and they try to argue that they're actually all consistent. And if you understand properly how the echoes models work, actually the fact that some groups say they see it and some groups say they don't is actually all consistent, because you need to be careful about which events you look at and how you look for them and exactly what you do and blah, blah, blah. And actually it's all consistent, and probably there is echoes.
And
That's
the phase of the moon today.
Sorry?
And the phase of the moon.
And the phase of the moon. Yeah. Yeah. So one of the things that they claim in that paper at the bottom is possibly it's a mass ratio effect. And you have to look at events that have a high mass ratio in order to see it. And events with lower mass ratios don't have these echoes, or the echoes aren't very strong, but they're stronger in high mass ratios. And if you pick out those events only that have high mass ratios, maybe you can bump up the significance somewhat in various different ways.
So has anyone tried 1905-21?
Yes, you guys have tried 1905-21. I'll get to that in a minute. The interesting one is 1908-14. That is the event that was the sort of 25 mass 2.6 X object in the mass gap with a mass ratio of around 10. For some reason, the LVC did not see it as a priority to run their echo search on this. So it's not actually in the LVC echoes publication, the one at the bottom, the GWTC2 echoes publication. It actually, there's a footnote where they say, we didn't run on this event because we didn't have the computational resources to do it. And from Abedi's, well, Ashordi, it's Ashordi really. From Ashordi's point of view, the mass ratio is the key. And 1908-14 was not run on by the LVC. Now I happen to know that Jahed has run on 1908-14, and he sees no evidence of echoes in 1908-14.
But he will never publish that.
Well, we will keep trying to persuade him to publish it.
Okay, so if any student wants to run on this, use
Yes.
computational resources to run on this,
Yes.
and get a publication saying there's nothing there.
If you guys have resources to run on 1908-14, do it. Definitely. Offspec knows how to do it. The codes are there. Just run it, point it at the data, find out what it is, publish, cite Afshordi. Nah, mass ratio doesn't make any difference. Yes, do that. No, actually, to be fair to Jahed, he does have a draft. He does have a draft, and I am kicking him up the backside to put that draft out. But he's also been working on other stuff. He's been working on that paper that came out yesterday as well. So he has things to do. Right, to give you a little bit of background of my publication with Offek, this Vestervek et al. Paper in 2017, we reran on basically using exactly the same method that Abedi and friends used to find their tentative evidence. We used basically exactly the same method. Our results actually weren't that different. Our significance was only different by a factor of 2. And when you think about how, you know, what people's belief in these things, factor of 2 in the evidence, it's not that much. The factor of 2 for us was lower. And Afshori at least can't understand why, when we basically got the same result as them, why we say there's no evidence and they say there's evidence. He didn't really understand this. And part of the reason, I think, and this Offek can also comment on, is that we looked at a number of things to see how you would distinguish what you're seeing and from noise. And what we were finding was the thing they found, and the thing that we also found some evidence for, it had a number of characteristics that you would think, this looks a little bit like noise. This is what you would expect if you were just seeing something in noise. In particular, if you run on injections, so you fake signals, you put fake signals into the data and you try to recover them, what you find is, as the amplitude of those signals goes down, eventually you're unable to recover their amplitude. This is the plot on the left, showing different injected amplitudes going down. You recover it fine when they're loud. When they get quiet enough, you suddenly you're not able to recover the amplitude anymore very well. And that is exactly where Abedi and friends were finding their amplitude for their echo signals. Also, the ring down time, the rate at which these echoes decay. Again, if you have very loud echoes, you recover it no problem at all. It goes up, but eventually you get to a point where the amplitude is so low that you can't recover this anymore at all. In fact, you end up getting always that the decay rate of the echoes is always around 1, and that is exactly what Abedi and friends were finding. So there were a number of things that are maybe a bit difficult to quantify that I think suggested to us that even though we were getting roughly the same number as them, that we thought this you couldn't distinguish this from noise. Just for Offek, this is a little bit of fun just for Offek. If you go to Wikipedia and you go to the article on firewalls, there is a little section about characteristics and detection. It mentions that Afshori and friends made a big fuss about maybe they had found some evidence for these firewalls. And then there is this statement that other groups searched and found that there is no statistically significant evidence for such echoes in the data. Reference 14. If you look at what that reference 14 is, that is Vestervek et al. Now, I didn't put that on Wikipedia, and Julian Vestervek, who was the student, who was the lead author of that paper, he says he didn't put it on Wikipedia. Somehow it ended up on Wikipedia, our work, as that story.
It wasn't me.
It wasn't you either. There you go, you see.
No.
Somebody, somewhere.
You know, we've made it as scientists now, right? We have a paper quoted on Wikipedia.
Yep, I know. It's good. Huh? It's good for Julian.
Yeah. Right.
This is the LVC's result. So the LVC, the LIGO Virgo collaborations, they ran on all of their events except 1908-14 and was it 15-10-12? I'm not really sure why they didn't run on 15-10-12, because that is the event that had the most evidence for echoes. I don't know if Offek was, so Offek is sworn to secrecy on these things, but I don't know if Offek was part of the discussions about this, but not running on 15-10-12 seemed like an odd decision when that is the one giving most evidence for echoes. And then also not running on 1908-14 when that is the one with the highest mass ratio, that Ashori is trying to tell everyone that if you have a high mass ratio, you get the most echoes. That was also an odd decision from the LVC there. I wasn't part of these LVC discussions. I don't know if Offek was. I don't know if Offek wants to comment on that, but I thought it was curious. And Ashori thought it was curious as well. So anyway, you see these.
I wasn't part of those discussions, and even if I were, I wouldn't say it actually on a recording with a flashing red light on.
That's true. All right, fair enough. So you see all these log base factors here. Most of them are negative, saying that it prefers no echoes to echoes. There's only a few that are positive, and the base factors are not very large. So this is why the LVC was saying, based on their results, no evidence of echoes. Forget it. There are some challenges with this. It is tempting to look through this list here and say, well, some of them, the evidence is actually positive. It's actually preferring echoes over no echoes. So where these numbers are positive, there is actual positive preference for echoes over no echoes. So maybe there is something special about these events. This one here, GW 190517 _ 055101. And some of these guys over here, I won't read out the numbers. Some of the ones that are positive, you might go and look and say, okay, well, maybe there's something about them. For example, this mass ratio or the total mass or the spin or the spins of the original events or something like that, and try and come up with a model based on that. As I say, this mass ratio one seems to be ruled out by Jarhead, at least runs on 190814, but you could try other things. There is this issue about modeled versus unmodeled searches. I'll say a little bit more about that. And in particular, there's this thing about what prior ranges do you use when you are searching for new physics, when you are looking for something that someone has never seen before, and you are looking without really knowing what you're looking for, what prior ranges do you use for the parameters? So very quickly, this is about the model searches versus unmodeled searches. The model searches require you to calculate a model so that you can actually calculate a probability in the model. If you think there are echoes, but you don't know what model you're looking for, you just think generally there have to be echoes because black hole information paradox or something, then what you need is an unmodeled search. If you think there are echoes and you know roughly what the model is, it has to be like this because theory says blah, blah, blah. Then you need a model search. You need to go away and calculate what you think is the actual model. And if you don't think there are echoes and you want to rule something out, which is the position that we were in basically with OFEC, then you need a model search because the model searches are always going to be more sensitive than the unmodeled searches. So if you want to rule something out and say people who have claimed there is this, there is not that, then you need a model search to show that it's not actually there. It isn't well studied how much better model searches are than unmodeled searches, but an equivalent, a rough rule of thumb from the binary black hole, standard GR binary black hole searches. There are modeled and unmodeled searches for those as well. And the SNRs that they're sensitive to are roughly about 8 for the modeled searches, roughly about 12 for the unmodeled searches. That means that you have something like a 3 or 4 times better probability, higher probability of seeing something with a model search than an unmodeled search for the standard GR binary black hole searches. They are more sensitive if you have a model. The other thing is about the priors. So I ran something also with OFEC again, where we used a model based on the Abedi model again. We assumed some prior ranges when we looked for the events compared to Low et al. Here on the right. You can see our prior ranges are much, much tighter than what Low et al. Were using, particularly the prior on, for example, the delta T echoes, for example, they went from 0.05 to 0.5. We went from this tiny range, 0.2825 to 0.3025, right? Our prior ranges were much, much tighter. And what that means is, if you assume a very wide prior range, you have a lot of parameter space where you're saying potentially a signal could be in this very wide parameter space. And what will happen is if you find a signal, but you only find a signal in a small part of your prior range, the fact that you've assumed a huge prior range for it will penalize your model by Occam's factor and will say the thing you have found is not very significant. So if you want to find a faint signal in the data, you have got more chance of finding it if you have a very tight prior range and you happen to get on the right priors, on the right parameters, than if you assume a very large range. The LVC, in their results, they don't actually say what prior ranges they used. That's also tut-tut, OFEC. But from reading the paper, I imagine they are using the same prior ranges that were used in this low et al. Paper, and these ranges are very, very broad. So in that sense, it's maybe not surprising that all of their base factors were so negative because you're assuming such a wide prior range. This is the last, almost the last slide now. Priors on theories, standard GR. You also need to have a prior on your theory, because really what you're doing a selection between is a model where standard GR holds and a model where standard GR does not hold. And the fun thing to think about is, what is the prior on standard GR model? How much evidence do you need to be convinced that standard GR is wrong? Right? This is not just a over a pint of beer kind of discussion. This is actually important because as we're going forward now, we can actually predict how much observing time we will have. We can predict how sensitive our detectors will be. We can predict how many events we will see. We can predict what constraints we will be able to put on these echoes models going forward. And if we want to be able to say we will be able to rule out a large part of parameter space or a small part of parameter space, we actually need to have some sort of quantitative idea of what are the real priors that people are posing on their belief in certain models. If you want to say how likely is it to convince the world that you have seen echoes in the future with, say, Lisa, you actually need some idea of what level of evidence do you need in order to be able to do that. So that is the end. This is slide 23 of 16. The conclusions, my opinion, again, there is no good evidence for echoes in the GW data to date. That doesn't mean it's not worth searching for. I think it's very well worth searching for. Also because you are probing right up to the Planck length from the horizon. This is something you can't do with the other tests of GR. Different models and different search techniques have been run by a number of different groups. There are people doing this. Whether they're getting consistent results or not is still open to debate. But the observational bounds that we have already provided are non-trivial. So something like 5% of the total final mass of the black holes is accreted after matter, after merger onto the black holes. And something like 90% or more of this now from an observational constraint is disappearing below 1 Planck length from the horizon. So there is quite a non-trivial constraint on all of this. So that is the end from me. I will happily take questions, if there
Alex,
are any.
I have a
Is
question.
Ofik there? Is Ofik disappeared again? Yes, there is a question.
Yes, Alex, it's Max asking.
Hi, Max.
Hi. First of all, really good talk. Thanks. The second question is regarding, let's say, the more theoretical intro that you gave.
Yep.
And let's assume that there are echoes. And if you can go back to slide 13. Yes, 13.
Slide 13, this one.
Yeah, exactly. So assuming that there are echoes, can you give some intuition regarding the shape of the envelope of the signal on the right plot that repeats itself after, I don't know.
Yeah. So the reason why the shape is changing is because
yes.
this angular momentum barrier here, that also the barrier on the inside, but also the barrier on the outside, it's acting like a high pass filter, and it is filtering out certain frequencies preferentially regards to other frequencies. And so this is slowly changing the shape of the signal.
Yeah, it makes it more symmetric, like around the center of the.
Yeah.
Okay.
But that also depends on what frequency dependence you assume for the reflectivity at the horizon as well. So you can have different models for the reflectivity of the horizon. Again, you could say, well, above this frequency, everything is absorbed. Below this frequency, nothing is absorbed, or something like that. And that will also affect the shape as well. And that is something you cannot calculate in GR. That's something you have to put in by hand or by some deeper model. Ofek, you're coming in and going out constantly.
I my phone died, battery died, so now I'm on Hallel's phone. But I've got 68% and Wi-Fi, so it should be stable from now on.
Right. We got to the end. I don't know if you saw the end. Max has just asked a question. Did I answer your question, Max?
Yeah, sure
Yeah.
did.
So Xiangyang had actually started working on this Echo idea and started trying out with PyCBC inference actually to get it to work. Xiangyang, do you want to say something as well?
Okay. I have a simple question. Can you hear me?
Yep.
In this slide, this is an unmodeled search. Is it right?
This one we're on now, 13, slide 13. No, this is a template. You could use this template to do a search with.
I mean this slide up this paper. This the slide you have showed.
This one with all the different searches. This has all the different modeled and unmodeled searches.
Slide 13.
Back to 13.
Slide 13.
This is slide
this is
slide 13.
So you mean unmodeled search? Is this an unmodeled search?
Yeah, this what is shown on the right, that is a template, that is a model. You could use that for a modeled search. If you want an unmodeled search, you would, for example, say, I don't know what the echo is going to look like, but it's going to repeat at some constant interval. So all I look for is some repeating signal at a constant interval.
So you mean this is model, this is template?
Yeah, this one here on slide 13, this would be, this you could use for a model search. Yeah.
Okay, thank you.
Any more questions?
I have a question.
Yes.
Not to myself, more to you, I think. So we put out this. Is this being recorded still?
Yeah, but I can turn it off.
You want to turn off the recording?
That's funny.
Let's just leave. The last bit in the recording is, let's turn off the recording.
I'm using I actually cannot turn off the recording because
You can't turn off the recording.
I am not connected from my own account now. I'm from Hallel's phone, which makes
So is it being recorded?
It is being
Don't
recorded.
know. Sorry?
It is actually Max Appelbaum is now the assigned host.
How is it being recorded on a phone that doesn't have any battery?
No. It's a cloud recording. It goes through the Zoom server, and it only needs the command on and off by the host. It never actually goes through a local machine. It's actually quite a nice mechanism. So, Max, if you would like to stop the recording, you are the host.
Let me check if I can do it. One moment.